Alright, so this is going to be a video about differentiability. And basically, for something to be differentiable at a point, these two things right here, 1 and 2, those two things right there must be true. So it has to be continuous at the point. That's what that first part says right here. It has to be continuous at a point. And you should already know the limit definition of continuity right here. And then also the derivative has to match on both sides. And I kind of have the equation right here for that. Now, it is really important to understand that it has to be continuous at that point. It's not just that the derivative has to match on both sides, because sometimes you can get a false positive for that. So you have to make sure that you actually test the continuity first before making sure the derivative matches on both sides. I'm going to show you an example to kind of illustrate this point a little bit. So we have this example right here where it's a piecewise function, and it says, is f of x differentiable at x equals 3. So the first thing I'm going to do is write down the limit definition of continuity and then start filling that in to test whether it's continuous or not at that point. All right, so the first thing I'm going to do is find this f of 3 value here, and I'm going to need the second piece because it says it's greater than or equal to 3 here. So I'm going to use this second piece, this 6x minus 9. I'm going to plug 3 in it, and once I do that, I'm going to get 9 for my answer. Okay, from there, I'm going to find the next part where it's the limit as x approaches 3 from the left. So I'm finding this part right here. Now, if you do that, we're going to have to use where x is less than 3. So we're going to have to use this first piece here for that one. So we're going to plug 3 in, square it, and you should get 9. So far, so good. 9 is equal to 9. Remember, all those three things have to be equal in order for it to be continuous at 3. So the last one, it says, so I'm using this piece right here, and it says the limit of f of x as x approaches 3 from the right. So we're going to have to use greater than 3, which we already did when we found f of 3 over here. So it's kind of easy because we're using that same piece because it's greater than or equal to. So this 3 from the right is going to be the greater than, but it ends up using the same piece as that f of 3. So far we have found that it is continuous at x equals 3. So right, continuous at x equals 3. So we have one of the stipulations for it being differentiable at 3 correct. Now we just have to test, is the derivative equal on both sides? All right, so for this one, I'm going to do the derivative of that top piece, the x squared, and it's equal to 2x. Okay, and it needs to be equal to the derivative of that bottom part right there, which is 6. Okay, well, x is equal to 3 here, so what we can do is just plug in 3, and you end up with 6 equals 6. So that shows that it is, in fact, differentiable at x equals 3. So the answer for the question, is f of x differentiable at x equals 3? You would say, yes, it is. Okay, one thing I really want to show is what sometimes students do is they just start with a derivative right away. So they would do they would skip to this green step right here first. So they would skip to this step first and go, yep, it's differentiable. But that can lead to problems because what if the first piece was still x squared, but the second piece instead was 6x minus 1. So I'm going to write that down really quick. All right, so by looking at this problem, you might think, oh, okay, I can do the derivative of the top like before, which is 2x, derivative of the bottom, which is 6, plug in 3, and you get 6 equals 6. And you might say, yep, it is differentiable, but it's not actually continuous because if you plug in 3 for these, you'll get 9, and since it's not 6x minus 3, so if you plugged in 3 at this bottom piece, you would get 17, and 9 obviously isn't equal to 17. So this would be not differentiable, so this would be no for this example, just because it's that 6x minus 1, it throws off the continuity. Now, one way of showing this, which is a longer way, but is using the limit definition of derivative. So that's what I'm going to do really quick here. So the limit definition of derivative, it would be, okay, it is important to note that we are going to be using this blue piecewise equation here for this example, just so everyone's clear on what we're doing here. Okay, so first thing we're going to do is do this right-sided limit right here first. Now it says f of x plus h, and h is greater than 0, so it's going to be a little bit above 3. So the piece that you would want to use is that second piece here. So we are going to say that f of x plus h is equal to 6x plus 6h minus 1. So that's f of x plus h minus f of x. F of x is going to be 6x minus 1, because plugging it in directly, you would need that equal sign 1 right there. So that's the one we're going to use. We're going to do some canceling really quick. 6x and 6x cancel, minus 1 and minus 1 cancel, and then the h over h cancels, and you end up with 6 on that side. Okay, the other side, we're doing it as h approaches from the left, so we are going to need the less than. So we're going to use this first piece for that f of x plus h. So we're just finding this part first here. And you're going to end up with x squared plus 2hx plus h squared. I'm going to put that in parentheses just to show the grouping. And then from there it says minus f of x. Now, if you remember, f of x is where it's greater than or equal to, so we have to subtract 6x minus 1. And then we're going to divide all this by h, and I didn't leave room for the limit as h approaches 0 from the left. So we have all these h's here, and nothing really cancels, so it's probably a good time to start plugging in x. Remember, we are still testing if x is differentiable at 3, so I'm going to plug in 3 for x. So if you plug in 3, you will get the limit as h approaches 0 from the left. You plug in 3, you get 9 plus 6h plus h squared, minus 18 minus 1 is 17, all over h. Okay, now you can see from this that things aren't really going to cancel. So we have the 9 minus 17, that'll be a minus 8. So now if you try to plug in 0 to this from this h, so if you try to do direct substitution, you end up with a negative 8 over 0, because this ends up being 0, this ends up being 0, and this ends up being 0. So you have negative 8 over 0, which is clearly not equal to 6. So this basically shows if you use the limit definition of derivatives, it actually shows that it's not differentiable. But remember, if you do that shortcut where you, like what I did right here, where I just found using power rule, it can lead to a false positive, because clearly the answer is no. And this whole thing right here basically proves that. It's because this 9, so let's zoom in here, this 9 right here doesn't cancel with this 17. Now if I kept this 6x minus 1 as 6x minus 9 from that original, from the original had 6x minus 9. If I kept it like that, then it would have simplified and you would have ended up with 6. And if you want, like, that's probably a good exercise. Try it out yourself and see if you do in fact get 6, and you will. So that's basically differentiability and how it relates to continuity. If you have any questions about anything in this video, let me know.